Today, kids, we're going to talk about one of the coolest substances that we can find on our planet. It's water. Miss Weinfelder, careful, that water has dihydrogen monoxide in it.
What? That's just water.
It's just water. Water is one of the most interesting substances we find on our planet. It is the only substance that exists in all three states of matter naturally. You find it as a solid in glaciers and ice caps, you find it as a liquid in the oceans, and you find it as a vapor in our skies and the clouds. 71% of our Earth is covered in water, and 60 to 70% of your body is made up of water, and you find it everywhere.
You guys may remember last year when we talked about chemistry, we talked a lot about water at that time. We talked about how everything in our universe is made up of teeny tiny little things called atoms. Yeah, if you guessed that before I said it, you remember. And atoms are made up of little parts called protons, neutrons, and electrons. They're built kind of like this, and in the middle we have a nucleus that contains positively charged protons and neutrally charged neutrons. And then way around the outside you have these little excited electrons that are negatively charged. The relationship of how many electrons each atom has is how atoms start adding together to form molecules. You may remember us talking about some atoms don't have as many electrons as they would like, and so they kind of kick around, wishing they had a few more electrons, hoping somebody would share with them. And in water, you have oxygen, which wishes it had a couple more electrons, and you have hydrogen, which wishes it had one more electron. And when they find each other, they're like, hey, if we shared, everybody could have as many electrons as we needed. And so they form these bonds and stick together called covalent bonding. And the oxygen ends up having a little bit more of electrons hanging out around it, so it makes it a little bit more negatively charged. And because the electrons are moving in that direction a little more, it leaves the hydrogen a little more positively charged because it's got its proton in there. And that makes the molecule very polar. What polar means is kind of like in a magnet where you've got a positive pole and a negative pole, and if you put a positive and a negative together, they attract and stick together. But if you try to put two positive poles together, they repel or push apart. And a water molecule is built exactly that way. It is polar. So when water molecules see other water molecules, the negatively charged oxygen is attracted to the positively charged hydrogen in the other water molecules around it, and they are attracted to one another and they stick together just like these two magnets in a bond called a hydrogen bond. The bonding of water molecules is called cohesion, and this cohesion lets the water molecules be flexible but stick together very tightly. Think about a droplet of water when you've got it rolling around on a piece of paper or a piece of glass. It sticks together. That's called cohesion, and water has one of the strongest cohesive bonds in any non-metal substance found on Earth. When we have a little droplet of water, the little molecules inside the droplet of water are sticking together. That's called cohesion. Good. And at the surface, they're sticking together with stronger bonds. And those stronger bonds are called surface tension. Those bonds can be so strong that sometimes they can hold up objects that would normally sink in water, like trying to float a paperclip on a cup of water, or you've seen bugs holding themselves up on top of the water before. They're doing that because of this surface tension caused by the cohesive bonds of water.
water does love to stick to itself, which is called cohesion. We can do a little experiment and watch it on this card. I'm going to put a few drops on here, and when the water rolls around, you'll notice they love to join together into a bigger drop. I used to look at this kind of stuff all the time on car trips when it was raining and watching the raindrops combine and race down the window. Now, water doesn't just stick to itself, which is cohesion. It likes to stick to other things, which is called adhesion. When water sticks to other things, like it loves to stick to my fingers and your body. This is why you get wet when you jump in a pool, because water adheres to you. Adhesion.
So you guys have all seen the commercials about which paper towel is the most absorbent, and absorbent is really just a fancy term for how well does the paper towel adhere to the water, or how well does the water adhere to the paper towel. So when paper towel is absorbing water, you have both cohesion and adhesion at work. You have cohesion, keeping those water molecules strung together, and then you have adhesion where they're attaching to the fibers in the paper towel. And so water will literally climb paper towel because it's adhering to the paper towel and then grabbing other water molecules, and their cohesion lets them adhere, their adhesion lets cohesion, adhesion, cohesion, literally letting those water molecules climb up the paper towel, which brings on an interesting experiment you could try at home. Cut a piece of paper towel and tape it to a ruler, and then put that ruler next to a container with some water in it. I've put a little purple food coloring in here so that we can see the water more readily. Make your first mark at the level of the water, and then make some other marks at equal increments up the ruler, and make a hypothesis or a scientific guess about how far water is going to climb up this paper towel. And that's kind of a measurement of how absorbent the paper towel is. So we're gonna stick this in here while we do some other experiments, and we're gonna let cohesion and adhesion do its work, and you can see it's already started. Cohesion, adhesion, cohesion, adhesion, cohesion, adhesion, climbing its way up the ruler. So we're gonna set this aside and do some other fun experiments, and we'll come back and check on this in a little bit.
Water's ability to adhere and cohere both to other things and itself is what allows plants to drink water. Now, plants can't absorb water on their own. They don't have a mouth to suck water or a circulatory system that pumps water through the plant body. You never see plants in the forest go, which would be creepy if you think about it. You walk into the forest and all the plants were...
Ooh, yeah, that'd be so scary.
Yeah, no, not for me. But they get water to them, to the top of these very tall trees through adhesion and cohesion. And we can demonstrate that with this little tube we have here. I am going to pour some water into here, and it will run through this tube and fill up all these other little tubes. Now, normally, the water level should be the same across all of these tubes, but these tubes have different diameters. They get smaller and smaller. So let's see our adhesion and cohesion, or capillary action, in action. Are you guys ready? Now, if you look very carefully, you'll notice the water level is very similar to this water level. But over here in the smallest diameter tube, the water level is actually higher, because the smaller the tube is, the better water can adhere and cohere and capillary action up the sides. And that's how plants drink water, because of adhesion and cohesion and capillary action.
adhesion and cohesion of water lead to some pretty impressive demonstrations. For instance, if I take this jar and I fill it full of water, a little bit. Again, we put some purple coloring in the water so it's easier for you guys to see at home. And then we take this card and put it over the jar. We can flip the jar over, and the adhesion qualities of the water molecules will actually hold this card on the jar. And then if I slowly remove this card, they will hold themselves together through cohesion and adhesion. Isn't that cool? I love that experiment. Let's watch that one more time. I'm gonna fill the jar with water. Put the card on top, flip it over. And the adhesion will hold the card. Now when I remove the card, the adhesion and cohesion in the jar hold the water molecules up into the jar. Now, there is something I am not telling you, and that is that in the lid of the jar, I have a screen mesh. And you've probably gotten screens wet before, maybe a sliding screen door on your home or the windows, and you'll notice when water gets on the screen, it fills up the little squares. And that's a beautiful example of cohesion and adhesion. The water molecules are sticking to the screen, adhesion, and they're sticking to one another, cohesion, which lets them fill the gap between the little strands in the screen. And that surface tension is so strong that it actually, if you give it a little bit of help so the water molecules don't tumble out immediately, allows you to hold the water in the jar. Now, if I tip the jar sideways, those little water molecules start rolling across each other and they can't hold on anymore. It's kind of like if you guys were all holding onto a rope net and I tipped the rope net up, and if one person let go, it would tumble down all of the other people and nobody could hold on anymore. And that's how it breaks the surface tension. Ton of fun to try that at home. All you need is a mason jar, and you just remove the metal lid portion and cut a little piece of screen and then laminate a piece of photo paper. If you have those supplies at home, you could try this out. It's a ton of fun.
There's a really fun demonstration and experiment you can do with just a paper clip and a couple of jars of water. And this is to show how strong surface tension is. A paper clip, which normally sinks in water, if you do it properly, you can have the power of surface tension help hold up this paper clip that would normally sink. Now I'm gonna fill this jar up almost to the tippy top. And if you look close, you can see the water level is actually a little higher than the jar, and that's the surface tension or the adhesion and cohesion of the water molecules holding on to each other. And if I'm gentle, I can take this paper clip and set it on top of the surface tension water molecules, and it should float. But you have to be really, really careful. Ta-da! Go play. Go play. Look at that. Amazing.
I want to poke it.
Poke it. Oh! You broke the surface tension and then it sank.
Ah! So cool, Mr. Kyle.
So let's check back on our jar with the ruler and the absorbent paper towel in it. And I have been watching it for the last half hour or so, and it kind of stalled right about here. Now, why would it stall? Why would it not keep climbing? And if you've ever held a gallon of milk, you know that liquids are pretty heavy and water is very heavy. So if I gave you a gallon of water to hold, you'd be like, yeah, this is heavy, but I got this. And then if I stacked another gallon of water on top of it, you'd be like, oh, this is becoming pretty heavy. And then if I stacked another gallon on top of it, now we have a column of water that has a lot of weight. And even at the molecular level, a column of water starts to get very heavy. So there's a force pulling down on these water molecules that are trying to adhere and cohere their way up the paper towel. What's that force that pulls things down to the ground? If you answered gravity, you're right. Gravity is pulling on these water molecules, and at a certain point, their ability to adhere and cohere is overtaken by the force of gravity pulling back down. And so it eventually stops climbing the paper towel. At home, it would be fun to try out two different paper products, like a napkin and a paper towel, and see which one is more absorbent or which one allows adhesion and cohesion to go on for longer before gravity takes over and it stops.
You can watch plants adhere and cohere with capillary action at home. All you need is a piece of celery, a jar of water, and some food coloring. And what I'm going to do is take this food coloring, drop it into this jar, and then I'm going to put my celery inside the jar. What do you guys think is going to happen with the celery and the colorful water? Go ahead and comment below if you think you know what's gonna happen.
Well guys, that's a wrap for Water Liquid Awesomeness!
Yay!
I hope to see you next week!
Bye!